And what the next type, we will see there is a topology maintenance mechanism. Based on that, we can classify the multicast routing. So mechanism of the multicast topology can be done either by soft state approach or by hard state approach. What is meant by soft state approach? So we know that continuously there is an updation mechanism for the whole routing, and there is a control packet sending. So as soon as the updation occurs, new route path is established. There should be control packets, that is RTS, CTS, and after data transmission there should be acknowledgement packet. So all these are control packets. So how the control packet is transmitted, depending on that the routing can be classified. So if all the control packets are flooded periodically, that means time to time control packets are being transmitted from the sending node to all the nodes. Okay, the sending node doesn't know whether anybody requires it or not, but just it does its duty that time to time. So after a certain periodic interval, all the updated node information is flooded. Flooded means transmitted in all the directions. Okay. So after a certain time, periodically, the control packet information is flooded throughout the network. So if that kind of thing happens, that is called as a soft state approach of multicast routing. And in hard state approach, what happens? In hard state approach, the control packets are transmitted only when a link breaks. So if the link is broken, then rerouting has to be done because data transmission was taking place through that link. As soon as the link is broken, some other path has to be established through which the data transmission can take place. But whenever a new path is being designed through that path between sender and receiver, again that RTS, CTS, all packet transmission, and after data reception, acknowledgement packet, all these things should happen. So whenever there is a new path, there should be this control packet exchange. So if the control packet exchange is transmitted only when the link is broken, then that approach is called as hard state approach. So very basic difference between soft state and hard state. In soft state approach, time to time, periodically after a certain time, without knowing who requires it, the control packet informations are flooded throughout the network. But in hard state approach, only when the link breaks, that time only the control packets are exchanged. Hence, in hard state approach, the control packet overhead is less, because if there is a link break, then only the control packet will be sent. If there is no link break, then means in hard state approach there is no sending or reception of control packets. So this is the difference between soft state approach and hard state approach of topology maintenance mechanism. So how the topology is maintained after it is broken. Okay, so in soft state approach, continuous sending of flood control packet is there after a certain period, but in hard state approach only on demand. So whenever there is a link break, then only the control packets are sent. So there is a very important difference. And in soft state approach, we find that control overhead is too high because periodically control packets are flooded. But in hard state approach, control packet overhead is very less because if there is a link break, then only the control packets are transmitted. So this was the classification, three types of classification of multicast routing. Then we will see what is meant by tree-based multicast routing, and one special routing protocol under a tree-based is called as BEMRP, that is bandwidth efficient multicast routing. So BEMRP is having three stages. All those three stages we will see. So this is kind of the only topic for today, that is tree-based multicast routing, and it's many tree-based multicast routings are there. Among them, we will see only one type of tree-based multicast routing, which is called as BEMRP. Now, what is meant by tree? What is meant by tree? That also we will see in BEMRP. So many nodes which are carrying information. So from the sender to the receiver, okay, all the nodes are connected through some intermediate nodes. So that total topology from the sender to the receiver, and maybe in between there is a branching. So after two nodes, that means there may be another path through which the sender is sending information to another receiver. Okay, so there may be one sender and two receiver kind of a thing. So all the intermediate nodes, one sender, two receiver, they are making a tree. So tree means it's an information transmission tree. Okay. So tree-based multicast routing protocol, what are the advantages, disadvantages, what is the type, how the route is formed, how the route is maintained, all those things we are going to see here. So tree-based multicast routing is a well-established concept used in several wired multicast protocol to achieve high multicast efficiency. What is meant by efficiency? How much data packet we are transmitting divided by data packet plus control packet. So this is a question which is frequently asked as a short question. Efficiency of routing is total data packet transmitted divided by total data packet and control packet transmitted over the network by this protocol. So in this protocol, there is only one path between a source and a receiver path. So this is tree-based multicast routing. The main drawback of this, there is no robust enough to operate in highly mobile or dynamic environment. So if there is huge node mobility, one node goes away from the actual tree or actual path, then the path breaks. And if the path breaks, at the time the communication does not take place between the transmitter and the receiver. So tree-based multicast protocol. So these are features of tree-based multicast that we are explaining. Tree-based multicast can be classified into two types. One is source tree-based, one is shared tree based. Okay, so in source tree based protocols, as it is explained previously, in source tree based protocol, a single multicast tree is maintained per source, whereas in a shared tree based protocol, a single tree means from sender to receiver with all the intermediate nodes. All this few nodes make a information tree. Okay, so in source tree based protocol, a single multicast tree is maintained per source. Okay, that means there is only one linkage between the sender to the receiver with intermediate nodes. But in shared tree-based protocol, a single tree is shared by all the sources in the multicast group. So it is already discussed in the previous slide of classification. In source tree-based multicast protocol, an increase in the number of sources give rise to proportional increase in the number of source trees. So number of data sources increases means in source tree based number of tree also will increase. So this results in significant increase in bandwidth consumption. In a shared tree-based multicast protocol, the increased in bandwidth usage is not as high as source tree-based protocol, because even when the number of sources per multicast session increase, the number of trees remain the same. Because in shared tree-based multicast protocol, one tree is shared by many sender and many receiver. So number of sender might increase in shared tree based, but that will again be using the same tree, and that will not increase the number of trees, that will not increase the number of bandwidths, that will not increase the control overheads. So this is a very important difference between source tree based and shared tree based multicast protocol. Here we are coming to one type of tree-based multicast protocol, which is called as bandwidth efficient multicast routing protocol. In short, it is known as BEMRP. A very important question for exam, so it can be asked for 10 marks. So there are many different ways the question can be asked. That is because this is there are three steps in this BEMRP. One is tree establishment, then tree maintenance. Okay, so there are different questions which can be asked, which we will discuss at the end of this session. So first, let us see what is meant by bandwidth efficient multicast routing. So bandwidth efficient multicast routing, short it is known as BEMRP, is the efficiency is the key design issue for the multicast protocol. So efficiency, again I will repeat, efficiency is total data transmitted divided by data packet plus control packet. BEMRP tries to find nearest forwarding node. So the logic behind the protocol, that sender node just tries to find out what is the next node where it can send data. That's all. Again, next node will see what is the next node to whom it can forward. So every node for forwarding just tries to find out where next it can give the data. That is the logic of BEMRP. So BEMRP tries to find nearest forwarding node from source to the receiver instead of the shortest path between them. So whenever a node is trying to find the shortest path, in that case it has to have a global understanding of the whole network. But in case of BEMRP, it doesn't need to check what is the shortest path between the sender to the receiver. It just checks in the direction of the receiver which one is the next node. So when I show you the diagram, you will understand. Okay, so hence the number of data packet transmission is less here. Hence the number of control packet transmission is also less here because it is more directive. It is not sending information to everybody. It is not flooding information. It is highly directive, and it is sending information only in one direction. To maintain the multicast tree, tree means from sender to the receiver, all the intermediate nodes connected, they are carrying the information, that is called as tree. To maintain the multicast tree, it uses a hard state approach. What is meant by hard state approach? Whenever link is broken, then only all the control packets are produced. In soft state approach, control packets are flooded periodically. Okay, actually that is increasing the control overhead. So in case of multicast tree in BEMRP, it uses the hard state approach. That is only after the link breaks. If the link breaks, then only a node transmits the required control packet if it wants to rejoin the group. So what is the point of transmitting the control packet? That is, if due to mobility the node went outside of the tree, then again it wants to come back. After coming back, it again exchanges the control information, control overhead, so that it can rejoin the group again and continue the data transmission. So only after the link breaks, a node transmits the required control packet if it wants to rejoin the group. That is actually the hard state approach of communication, transmission, link establishment. It avoids periodic transmission of control packet, that is actually soft state approach, and hence a lot of bandwidth is saved. So there is a feature of BEMRP. To remove the unwanted forwarding packets, route optimization is done. So I was telling you there are three steps. First one is route establishment or tree initialization. Okay. Tree means, again I'm telling you, it's a connection between the sender and receiver with a lot of intermediate nodes. Second step is tree maintenance. That means if there is a link breakage, then how again that link is maintained. So link break occurs due to node mobility. So first step is tree initialization, how one receiver can be a part of the whole existing tree or the whole network. Second is tree maintenance, if there is a breakage of link, how the another path is re-established, that is actually tree maintenance. And third thing is tree optimization, very important stage, that is optimization means remove of unwanted forwarding nodes. So you are reducing the number of node means you are reducing the number of control packet, data packet. You are reducing number of unnecessary transmission to these nodes. Okay, so all this actually optimizes the data packet. All this optimizes the power in the whole network. So these are the three steps, and all these three steps are having certain diagram. I have drawn the diagram, exactly the same diagram you have to draw in the exam. So I have shown the diagram 6, 7 in different slides. You have to draw only one diagram for tree initialization, one diagram for tree maintenance, and one for tree optimization. Try to understand the concepts because this is a very important question for the final exam. See the node, see the network, giving you some time. There are only three types of nodes you can see. So all these white nodes, they can be node, or some white nodes are there which are not given any kind of name. So they are actually non-participating node. You can check here. So this is a non-participating node. This is a non-participating node. Each of this node is having different features. So each of this node is having feature of sensing, and then microcontroller, then communication, then they are having battery with it. So all these are hardwares connected to each of this node. This is a sender node, this is sending information, and this is a tree. Okay, so whatever is shown here, between this yellow sender to receiver R1, there are two intermediate nodes. Okay, so they are called multicast tree node or intermediate node. This pink type of things, they are intermediate nodes. So there is a tree, this tree is having one sender and two receivers. And there are a lot of nodes which are not taking part now, but in due time you will see that they are also taking part. So what is written here, in this case R1 R2S forms a multicast path from the beginning. Okay, so there is one sender and two receivers, so that's why this path is a tree, this path is a multicast tree. Okay, and they are non-participating nodes. Here R3, which is a new receiver, it wants to join the multicast group. Okay, so what's happening here is this sender is actually sending information to receiver 1 and receiver 2. Now this receiver 3 feels that it also wants the information which is being sent by sender S. But there is no intermediate path between sender and receiver R3. That has to be that path has to be established, or that tree has to be established. So here R3, so this is called tree initialization. That means if this R3 wants to receive information from S, how is the intermediate nodes will be activated, how this tree is established, this is explained in this first process in BEMRP, which is called as multicast tree initialization in BEMRP. Why is called multicast? Because there is one sender and many receiver. Okay, so there can be many sender and many receiver as well. So here agenda is R3, a new receiver wants to join the multicast group. So this is the R3 yellow one, this is a new receiver, and as R3 would like to receive data packets from sender S. So here BMRP tree construction is initiated by R3 receiver. So I told you there are two types of, again there is another classification of routing, that is whether it is source initiated or receiver initiated. So this is a receiver initiated single tree kind of a multicast routing. Okay, so here BMRP tree construction is initiated by the receiver. How to do it? So R3 wants to join the multicast tree. How the process is done is explained here. What happens is, so as R3 wants to join this group, R3 wants to receive information from S. What R3 does is, so there are mainly three kinds of nodes here. So these white nodes are called non-participating node. These pink nodes in between, they are called multicast tree node. Yellow nodes are called as multicast group members. So multicast group members are either sender or receiver, and this pink kind of nodes, they are intermediate nodes. They are actually connecting the multicast group members, which are shown in yellow. How the R3 joins the group? Okay, so by hardware, microcontroller based hardware, by acknowledgement, RTS, CTS, we have to do this. So that process is explained. So here you can see a new packet, new direction of packet, a new packet which is called as join control packet. So whenever the R3 wants to join this group, R3 wants to be a multicast group member, R3 wants to receive message from S, R3 receiver will flood the network with join control packet. So join control packets are going from R3, just check the arrow direction, to any direction, okay, and it is hitting what is the next multicast group member or multicast tree node. So just see the path. So from R3 through I8, I8 means node 8, I means identity. So I8, I7, I6, I5, I4 sender. So this is one path through which the R3 can receive information from S. Another path can be R3 to I12, I11, okay, then this can be I10, okay, then it can be R2, and then it can receive information, because when R2 is established, then this S through this path, so S through all other intermediate paths through R2, through I10, I11, I12, it can receive information. Okay, like this. So and another path is R3 to I3 to I2 to I1, and that's it. So whenever it is connecting to I1, means I1 is already connected to sender. Okay, so in that case, if R3 is connected to I1, means S, and through all these nodes, R3 will be able to receive information from S. So what is this stage now? R3 receiver will join. R3 receiver will flood the network with join control packet. So join control packet will go from R3 to all upward direction. Okay, so all upper nodes are called as upstream, and below nodes are called as downstream. These packets will be received by nearest multicast tree nodes and multicast group members. So this is a multicast tree node, and this is yellow is a multicast group member. R2 is also a multicast group member. So here S, I1 and R2. So this is S is a multicast group member, I1 intermediate node, and R2 it's a multicast group member. They all will receive the join control packets. Then what happens upon receiving all the join control packets, this R2, I1 and S, they know that somebody is asking for the contention. Somebody is asking to join the group. So what S, I1 and R2 will do? S, I1 and R2 who received the join control packets previously will respond with a reply control packet. Okay, so reply control packets are given by blue and direction is reverse. So you can check that this green joint control packet is going from bottom to top. So from R3 it is going towards S, but this reply control packet are coming from multicast tree node and multicast group node toward the R3. So it is like of a so this joint control packet can be somewhat like RTS, and reply control packet somewhat it can be like CTS. Okay, so the step is R3 wants to join the group. So first R3 floods the network with joint control packet, which is shown in green. Upon receiving that, all the multicast tree node and multicast group member, they will respond with a reply control packet, which is given in blue. So the direction of the reply control packet are from the multicast tree and multicast group nodes toward the new receiver node R3. So R2 and R1 is already a member of the tree which is receiving information from S, but R3 wants to receive information from S, but there is no path. So that path establishment is called as multicast tree initialization. So what is the first step? R3 first sends the joint control packet towards the multicast tree node, multicast group node. Upon receiving that, all the multicast tree node and group node sends back a reply control packet to the receiver in a shortest path. Now check that R3 sent a joint control packet to I1. Okay, just check. R3 sent joint control packet to I1 in two paths. So first R3 sent to I3, then I2 to I1. This is one path through which R3 is sending joint control packet to I1. Another path between R3 and I1 is R3, I8, I7, I6, I9 and I1. So another path of joint control packet between R3 and I1 is I8, I7, I6, I9 and I11. Upon receiving this, I1 understands that R3 is trying to reach I1 by two paths. One path is through I2, another path is through I9. But I2 path is having 3 hop counts and I9 packet is having 1, 2, 3, 4, 5 hop counts. So I1 receives joint control packet request from R3 through two paths. One is through I2, 3 control hops between I1 and R3, and another is through I9, that is 5 control hops between I1 to R3. While sending back the reply control packet, I1 will send the reply control packet through the shortest path. That means I1 will send back the reply control packet through I2, I3 and R3. So there is no reply control packet shown in I1, I9 path. Just check. Okay, so there is a very smart kind of control action. So whatever sender, when it received the joint control packet, it had sent the reply control packet. How many hops? 1, 2, 3, 4, 5 and 6. When this R2 received joint control packet, how many hops it sent the reply control packet? 1, 2, 3, 4. Okay, so they had all sent reply control packets, but this I1 who received joint control packets from R3 through two different nodes, I2 and I9. I1 understands that I9, I6, I7, I8, R3 is a longer path compared to I1, I2, I3 and R3. Hence, I1 will send the reply control packet through I2, I3 and R3. So these are the features which you have to explain very clearly in exam in detail. Okay, so here again R2 sends it back to I10, I11, I1, I12 and R3 like this. Okay, so first R3 will send all the joint control packet, and upon receiving that, multicast tree node and multicast group member will send back the reply control packet. So all the reply control packet now comes to, so reply control packets are sent back by the tree and group nodes upon receiving the joint control packet and after waiting for a small specific time. So all the S, I1 and R2, they received the joint control packet, they waited for a certain time and then they have sent the reply control packet. For sending back the reply control packet, the tree nodes choose those paths with the smallest hop count traveled. So I explained that this node I1 could send the reply control packet to R3 by this path through I9, I6, I7, I8 and R3. But there are 5 hop counts. Okay. But same path I1 to R3 is done by 3 hop counts. Hence I1 discards this path and I1 sends the reply control packet through this lower hop count path, that is I1, I2, I3 and R3. So that is what is said here. For sending back the reply control packet, the tree nodes choose those paths with the smallest hop count traveled. Many reply control packets reach the requesting node R3. What R3 is trying to do is R3 is trying to establish a connect between R3 and S. So if R3 can connect to I1, then itself job is done. Because if R3 is able to connect to I1, then S to this node, to I1, to I2, to I3, to R3. Then R3 will be able to receive information from S. So either R3 has to connect to R2, or R3 has to connect it to I1, or R3 has to connect it to S directly. So there are three paths. Just check the three paths, blue reply control packet path. So this three can be the path through which the R3 can receive the information through S. Thus, which path R3 will select? That is the shortest path between R3 and I1. So R3 will again finally send. So first it had sent the green packet, join control packet. Then it had received the blue packet, that is reply control packet. So upon many reply control packets now reach the requesting node R3. R3 has to choose one of the path and send reserve packet on that path. So what is the reserve packet doing? Reserve packet is actually establishing the final path between the R3 and to a intermediate node or to a multicast group node. So that is what it's doing. So first step is sending of control packet from, sorry, first sending of joint control packet from the R3 towards all the tree node and group node. Second step is all those tree nodes and group nodes will send back the reply control packet, so the shortest path. Okay. And third step is whenever all those reply control packet come to the R3, then R3 has to reserve one of those many paths, and that path will be final, and that path will be the tree initialization path. So many reply control packets reach the requesting node R3. R3 chooses one of those paths and send reserve packet on that path. So R3 has chosen this path, that is R3, I3, I2 and I1. This is the shortest path because other paths are I12, I11, I10, R2. So there are 4 hops, and this path from R3 to S is 6 hops. But from here to here I1 there is only 3 hop, and if this path is chosen, then the information from S to R3 will come very easily. So R3 selects the lowest hop count path from R3 to the multicast tree or multicast group node and sends reserve packet on that path. So which was the initial tree? Initial tree was only S and these 3 intermediate nodes and R1 and R2. So R3 wants to join this group, means R3 has to touch the nearest tree node. So nearest tree node is I1 because this is having 3 hop count. So that we can see here. So this is the whole process of tree initialization. The last thing, R3 selects the lowest hop count path from R3 to the multicast tree or multicast group node and sends reserve packet on that path. So tree initially was S, R1, R2 and this intermediate node. R3 wants to join this tree, and now there is another tree produced. So tree has now having a different new branch. Okay, so this is the same single tree because this is tree based multicast routing protocol, but now the tree has developed a new branch. Okay, so that new branch is going towards the receiver R3. So R3 selects the lowest hop count path from R3 to the multicast tree or multicast group node and sends reserve packet on the path. Now here there are some features. First feature I have already told. Tree node I1 receives joint control packet from I9 and I2. Okay, but I1 sends, that is this tree node, it sends back the reply control packet only through I2, because I2 and not through I9 node, because I1 to R3 is only 3 hop count, and I1 to R3 through I9 is 5 hop count. So as this is a smaller part, the reply control packet from I1 to R3 comes through the smaller hop count. So this is a very important thing. Second important thing is receiver R3 receives reply control packet from source S, receiver R2 and intermediate I1. So these blue packets are sent to the R3 by sender S, I1 intermediate node and R2 group member. So all the 3 of them are telling R3 that yes, you can join the tree through us. But as reply control packet sent by intermediate node I1 has only 3 hop counts from I1 to R3, R3 sends reserved packet for I1 node through I3 and I2. So this path, this black path is now selected, and this is the way the R3 receiver joins the group. And now the tree becomes S, R1, R2, R3, and there are 1, 2, 3, 4, 5 intermediate nodes. So this becomes the new tree now, and this is called as tree initialization step. Second is, so here you can see the tree. So now the tree is already established. So here there are three receivers, R1, R2, R3, and there is only one sender, and there are 1, 2, 3, 4, 5 intermediate nodes. Now the question has changed. So now this is second part, which is called multicast tree maintenance phase. Okay, so multicast tree maintenance is the process of establishing connectivity after a link breaks due to receiver node mobility. Okay, so what I'm showing you is now receiver is at position A. So this was the R3 position. What's happening is, let's assume that receiver R3 is moving now. Okay, so what's happening that receiver R3 is moving, and receiver R3 is now moving from A towards a lower position. So R3 is coming down. Okay. What we find is due to node mobility, so receiver node R3 has now joined the multicast group, and it is communicating properly from position A through I3, no problem. But due to node mobility, so here starts the tree maintenance. Actually, link breaking happens first and then tree maintenance. So due to node mobility, the R3 has shifted from position A to position B. So the cases you have to create first, and then you have to explain how to solve it. So initially R3 was not there, so now R3 is there, the tree is there, R3 was transmitting, receiving data perfectly. Now what happens, due to node mobility, R3 has shifted below. R3 has shifted below means from position A, that's why it is shown as by dotted lines. So from position A, R3 now has come to position B. That means previously this R3 and I3, this link was there because this was one hop count, maybe 10 meters. Okay, but this A has now come very far. Now this distance may be 50 meters. Okay, so previously position A and I3, this was maybe 10 meters. Now this R3, because of its mobility, has come out to a great distance. So now the new position B and I3, this distance is quite a lot more than 10 meters. So this distance may be 50 meters. So then there cannot be a link established directly between R3 and I3. Now how this R3 will establish contact with the S, or now how the R3 will establish contact with I3, this is the question. Okay, so this is actually solved by tree maintenance. Let's see how it happens. So communication link between R3 at new position B and I3 node is now broken. So previously I showed you. So this was the previous position of node R3. Now R3 is moving. Okay, as R3 is moving, it has come to its new position, and this new position I3 is quite far off, and now there is no link between R3 at new position and I3. So now don't consider R3 at position A because R3 is not position B. Now exactly communication link between R3 and new position B has to be established. Okay, because R3 and B previous thing is over. Now multicast tree maintenance helps to regain communication from R3 through I3 and other node. So R3 now directly cannot connect to I3. It has to maybe take the help of I4, maybe it has to take the help of I6, I5 and all. So there's a new way of establishing communication between R3 and I3. So that process is called as multicast tree maintenance phase. Again, there will be exchange of control packets, and these are actually control packets which are being exchanged because a new connection has to be established. And why new connection has to be established? Because there is a movement of R3 node from its previous position to present position, and this new position has given rise that previous contact is all broken. Now also R3 wants to receive data from sender S. That means R3 has to establish a contact with I3 and with some other node. How that process happens, that is actually called as multicast tree maintenance. What happens to reduce the control overhead, the BEMRP tree reconfiguration is done only when a link break is detected. Because I told you this is a hard kind of So there are mainly two types. One is soft approach, one is hard approach. So in hard approach, whenever the link is broken, then that reconfiguration is done only when the link break is detected. There are two schemes to recover from the link failures. So there's the first scheme we are explaining. So as soon as the R3 comes to a new position, what I3 will do is I3 will send some broadcast multicast control packet. So this is actually the joint control packet kind of a thing. That's what I have kept the sign same or symbol same. So this is the first scheme. So when R3 has come to its new position, how to establish the link between R3 and I3? It can be done by two methods. One is broadcast multicast scheme. So what is that? The upstream node, upstream means which is above. So upstream node I3, which is closer to sender S. Downstream is which is far away from sender S. So R3 is a downstream node and I3 is an upstream node. So for link establishment, there are two schemes in broadcast multicast. The upstream node I3 is responsible. So I3 is now sending the joining control packet because R3 has gone too far. So I3 has to fetch the R3 and send it to R3. So R3 will send the joining control packet to I3. So I3 will send the joining control packet to R3. And then R3 will send the joining control packet to I3. And then hello. Okay, so what has happened here is to reduce the control overhead, the BEMRP tree reconfiguration is done only when a link break is detected. So whenever a link break is detected, then only we are going to send all the control packets. And who is sending the control packet? Here I3 is sending the control packet in every direction. So I3 will be sending the control packet to all the other nodes who are there in downstream. So I3 will send the control packet to I5, I5 will send it to I6, and I6 will send it to R3. Because main job of I3 is to find the R3 node, because R3 has gone in a new position and R3 has broken the contact. And again, there will be another path of broadcast multicast control packet that will be from I3 to I4 and to I4 to I3. So from I3 to R3, okay, from I3 to R3, there are two paths. One path is I3, I5, I6, and R3, and this is having 3 hop count. And another is I3 to I4 to R3. There are 2 hop counts. So broadcast multicast scheme, the upstream node I3 is responsible for finding a new route to the previous downstream node R3 for its new location. Movement or R3 from A to B isolated it from the remaining part of the node. So movement of R3 actually from A to B isolated it from remaining part of the tree. The upstream node I3 now floods broadcast multicast packet, and then after receiving this packet, R3 decides how to join I3, whether to join by this path, that is through I4, or to join I6, I5 and I3. Now R3 finds that if it joins I3 by I4, there are only two hop counts, and if it joins I3 by I6, I5 and I3, there will be three hop counts. So obviously after receiving this packet, receiver R3 send a reserve control packet through the smallest number of hop count path and rejoins the group. So R3 will now send this black packet, which is called as reserve control packet, same as the previous tree initialization stage. So R3 will now send this reserve control packet to I3 by the least hop count path. Least hop count path is R3 to I4 to I3. So I'll just explain this process again. So what was the first step? First step was first process was this S, R1 and R2. There was the tree and it was having three intermediate nodes. Then this R3 wanted to join this tree, so that was called tree initialization stage. So I3, I2, I1, so a new path was new branch was established through tree initialization, and R3 became a part of this whole multicast tree. Okay, and this is a tree for communication, and R3 was communicating very well with the other receivers, and it was receiving data from sender S without any problem. What happened next? Then that was actually tree initialization process. What is meant by tree maintenance? R3 is actually a moving node. What happened? R3 started moving from R3 position A to R3 position B. As soon as that happened, the link between R3 and I3, it actually went off, because now R3 has come in at a distant position. Now I3 has to find out where R3 is, and I3 has to take the initiative to establish the connection with R3. How it can happen? It can send, I3 can send same broadcast multicast packet. So there are two methods. In the first method, I3 is sending broadcast multicast packet to R3 via the intermediate nodes. So one path can be I5, I6, R3, another path can be I4 and R3. Then R3 checks that by which path it should go, which will be a lesser hop count up to I3. So R3 finds that if it is passing through I4, then it will be to a lesser count to I3. Then R3 actually sends a reserve control packet to I3, and via I4 the reserve packet is sent, and the connection is established. So now the new path of the tree will be R3, I4, I3, I2, I1, and the sender will be connecting accordingly. Okay, so this is the first path, this is the first type actually, which is called as broadcast multicast scheme. As a second scheme, so previous case I3 was sending the broadcast multicast packet. In this case, second scheme, which is called as a local rejoin scheme. In this scheme, the downstream node, so previous case the upstream node I3 was sending the broadcast multicast packet, because downstream node R3 had gone to some other direction. But in second scheme, this is also a tree maintenance, this is a second scheme. Here, local rejoin scheme. In this scheme, the downstream node R3 with the broken link tries to rejoin the multicast group by limited flooding of join control packet. Okay, so R3 now will send the join control packet, but that will be a limited transmission, not to everybody R3 will send, but to few nearby nodes, the R3 will send the join control packet. Same thing that happened previously. Okay, so one packet from R3 will go from R3 to I6, I5 and I3. Another packet from R3, green packet, will go from R3 to I4 and to I3. Now I3 will check which one is the smaller hop count from I3 to R3. So I3 will find that through I4, if it goes, this is the smaller hop count path. That means I3 will now send the reply control packet through the smaller hop count path, that is I3 to I4 to R3. And upon receiving that hop count path, R3 acknowledges this path through I4 and I3. So exactly the thing we found in case of tree initialization, the same thing comes here. And so when tree node I3 and I4 receive the join control packets, they send back the reply control packets. After receiving the reply control packets, the downstream node R3 rejoins the group by sending a reserve packet to the new upstream node I4, and it goes through I3. So new packet is sent to I3 and it goes via I4. Okay, so likewise. So there is a second scheme which is called as local rejoin scheme. Difference between previous, that is broadcast multicast scheme, is I3 sends the broadcast multicast packet, I3 initiates the process here, and in second case, local rejoin scheme, downstream node, that is the R3 node, it generates the join control packet, and then the other packets follow the suit, and the same thing happens. Okay, so who is initiating the process? So if intermediate node is initiating the process, it is called broadcast multicast, and if the shifted or moved out or mobile node initiates the process, it is called as local rejoin scheme. Last point today is multicast tree maintenance phase. What is meant by tree maintenance? Okay, and it is not actually tree maintenance. I'm very sorry. This will be tree optimization phase. So I'll just change it. There is a second part, and third part will be tree optimization. There is a third part which will be tree optimization phase. What happens at pre-optimization phase is, if the node is moving and if the node is moving up and it has gone to a very up position, okay, so it was down, now R3 node, now it has gone up and R3 node has gone to this position. Just check. Okay, so previously R3 node was here, it had come down, now R3 node has gone up. So R3 has come very close to sender S, or R3 has come very close to the intermediate node I2. Then what happens? So when a tree node or receiver node comes within the transmission range of another tree node, okay, then unwanted tree nodes are cropped or cut by sending a quit message. Okay, so now previously the RC node was here, it was connecting through I4 to I3 to I2 to I1, and then it was connecting to the tree. Now by movement, because R3 is moving, okay, previously R3 was at position A, then it had come to position B. Now R3 is moving further, and after moving it has come to position, now new position, so new R3 position it has come to. Now you can check that all this previously established connect, that is link between IT to I3, link between I3 to I4, all those links are of no use. Okay, so those links has to be cut now. That is the point. Okay, so how to cut it? So optimization, tree optimization means you have to optimize the number of links. That means links should be as less as possible, because more is the number of link, more is the transmission power. More is the transmission power, more is the wastage, and less will be the node lifetime. So if you want to save the node lifetime, if you want to increase the network lifetime, in that case, we have to reduce the number of link, that is communication link. Okay, so how can we crop or how can we cut off some of the communication link? That can be done by quit message. Okay, so how to generate that quit message? So when a tree or a receiver node comes within the transmission range of another tree nodes or intermediate node, then the unwanted tree nodes are cropped or cut by sending the quit message. Here R3 moved within the network and it comes within the transmission range of intermediate node I2. So R3 was previously down, now R3 has come very close to intermediate node I2. So hence this I2 I3, I3 I4, I4 I5, R3 I5, all these connections are of no use. Okay, R3 now will receive a multicast packet from the node I2 sooner than it from node I5. So this R3, as it is close to I2, very easily it can receive a multicast packet from I2 and not through I5. That means R3 will be very closer to I2 than I5. Okay, this is what the second paragraph is meaning. After receiving a multicast packet from node I2, so this I2 is sending actually a multicast packet to R3. After receiving a multicast packet from node I2, R3 sends a reserve packet to node I2. So R3 sends a reserve packet to I2. That is, R3 is directly establishing a contact with node I2. And that is not enough. R3 is telling I2 that yes, I am establishing a link with you directly. So reserve packet means R3 is reserving this path, direct path through I2. And that is not enough. What more R3 is doing is, R3 actually is sending a quit message to I5. So this quit message, quit control packet is actually given by this purple line. Okay, so this third paragraph is very important. After receiving a multicast packet from node I2, R3 sends a reserve packet to node I2 to set up a new route directly with node I2. R3 also sends a quit control packet to node I5, and then this I5 actually is forwarding this quit control packet to I4. I4 is forwarding this quit control packet to I3, and I3 is forwarding this quit control packet to I2. So since R3 is no more a downstream node of I5, node I5 forwards this quit control packet to I4, I4 forwards this quit control packet to I3, I3 forwards this quit control packet to I2. And on all the unnecessarily generated links, that is from R3 to I5, I5 to I4, I4 to I3, and I3 to I2. So all these four links in the next step will get automatically dropped. They will get automatically inactive, or they will get automatically broken. So this unnecessary forwarding nodes I5, I4, I3 will automatically get cut off, and the link between R3 to I5, I5 to I4, I4 to I3, and I3 to I2, they also will become deactivated. This mechanism helps to reduce the number of control packet. This mechanism will help to reduce the number of nodes which are not required for transmission, because now R3 will directly be transmitting to I2, and R3 will receive information from S through I2, I1, and this intermediate node. So through three hops, R3 is now going to receive information from S. So this is the loop. Okay, so this is called multicast tree optimization phase. Okay, so that's all. And BEMRP advantages and limitations. So advantages, the main advantage of this multicast protocol is it saves a lot of bandwidth by reducing the number of control packet transmission and reception. So this is actually saving the bandwidth due to the reduction of the number of data packets transmission, actually control packet transmission, and it is actually using the hard state approach of multicast routing. That is, when the path is broken, then only you send the control packet. So don't flood the control packet throughout unnecessarily. So if there is a breakage in the path, then only you send the control packet. What is the limitation? Since a node joins the multicast group through a nearest forwarding node, the distance between the source and receiver increases. You have seen that when the new tree was initialized, at that time the distance between the source S and receiver R3, it becomes quite long. So this increases the distance probability of path breaks. As tree becomes bigger, number of links become more, path break probability also becomes more, which in turn give rise to an increase in the delay and reduction in the packet delivery ratio. Also, since the protocol uses the hard state approach for route repair, considerable amount of time is spent by the node in reconnecting to the multicast session, which adds to the delay in the packet delivery. So in small, I will explain these two limitations to you. So advantages, as it is using hard state approach, it is actually using less number of communication or control packets. That is actually saving the bandwidth. That is the advantage. A limitation is, as the tree is growing, at that time number of links are becoming more. If number of link is becoming more, at the time link failure probability also is becoming more. So that is what is there. If link probability link is becoming more, means long tree length is responsible for actually delay in the packet transmission. So from the transmitter to receiver, the packet is transmitted and it takes quite a lot of time, and it is saying that it is increasing the delay and reduction in the packet delivery ratio. So this is one problem. Second problem is, since it is using the hard state approach, considerable amount of time is spent for link recovery, because when the link is recovered, then again if you are using broadcast multicast thing, so first broadcast multicast packet is transmitted, then R3 receives it, then it gives back the reserve packet, then link is established. So all these processes are taking time. Okay, since it is using hard state approach, considerable amount of time is spent by the node in reconnecting to the multicast session. So during this time, whatever data packet is produced, that will be lost, because there is no connection between the receiver R3 and sender S. So even if sender S is trying to send data, because of node mobility, R3 has gone out, and as long as it was trying to establish the route for that period of time, whatever was the transmitted data from S, that will be lost. Okay, so these are the two limitations, but moreover, BEMRP is a highly advantageous kind of a transmission. So that's all. That is the end of the multicast routing protocol. This is tree-based multicast routing we have done. Mesh-based multicast routing we will see. This is also in the same line, but yes, it is little different because mesh-based, all nodes are having connectivity with everybody. So if get time, I will do it. Otherwise, we will only go on with tree-based multicast routing. Okay, that's all from my side. Thank you.